all, welcome back to the session on the topic Principal Component Analysis. In this session, we are going to discuss about dimensionality reduction, variance, covariance, covariance types, and eigenvalues and eigenvectors with solved example. Credits to NPTEL, Luis Serrano, Serrano Academy, Dr. Balasubramanian R from IIT Roorkee. Consider the data set. We have n number of datas, and for this particular data, we need to take a photograph. So if you need to take photograph of the particular picture, you can take it from any angle. We have a number of angles. So angle 1 is here, angle 2 is here, but which angle takes maximum data? So a clear picture from which angle you can take maximum angle. So if you for this particular example, so this side, this angle makes a perfect example to take picture of all those. So now you can take a picture of this particular image. So you could able to get maximum data. So what's meant by dimensional reduction? Dimensional reduction in simple way we can say it is taking a picture of a particular data. So consider this data, and for this particular data we need to take the picture. So how we can take? So for each day if we take the picture of this particular data, so all those data will come and lie on the particular line. So all those data are projected on the particular line. For the same data, now I am going to change the position of the angle of taking photograph of the particular data. Now all those data will come projected on the particular line. Out of these two lines, we are going to say which line is taking more data. So right, taking which is clear and without affecting the projection. So this second data, this second image takes clear picture of the particular data. So this is dimensionality reduction. So in first image if you see all those data are overlapped to one another, but in second image it is not suited one and it is best suited for dimensionality reduction. So in house price prediction example, you can consider a number of data input features like size of house, number of bedrooms, number of bathrooms, number of floors, schools around the house, city distance from the particular house, and crime rate in the particular area. So if you have a number of features, in these features let me separate into two category. One is size of house, number of bedrooms, number of bathrooms, and number of floors are related to the particular house. So I am taking it as size feature. And remaining features are schools around the particular house and city distance and crime rate in the particular area. So all those features are related to location features. So for this example, instead of size of feature, you have four input features. For very easy purpose in 2D view, I am consider only size and number of number of rooms for our easy understanding purpose. So if you plot the data, it will look like this. So for this data, I need to project on a particular straight line. So this straight line indicates not a linear regression line. This line indicates a projection line. So if you project all those data, predicted data on the particular line, so the data will be little bit vary from its own prediction value. So but if you look now, the 2D data is converted into a single dimensional data. That is in 2D we have considered size and number of rooms, but now we have considered it, now you got it as a size of feature here. Now what is in by variance? How spread out a given data is? For example, consider this center point 0 and you have 3 points. One is at 0 comma 0 and another one at 1 comma 0 and another one is minus 1 comma 0. What is the actual distance from the mean value? What is the actual distance from the center mean? So it is 1 square plus 0 square plus 1 square divided by total number of data is 3. So you will getting 2 by 3. Same way for this example, 5 from left hand side you have again 3 data are there. From left hand side is 5 square. How much distance it is varied from the mean? It is 5 square plus 0 square plus 5 square divided by 3. So you will get 50 by 3. So for this particular data again you have the mean is 3 and you have 3 data and the mean of first data is 2 and the second data is 1 and the mean distance from third point with respect to mean is 3. So it is 1 square plus 2 square plus 3 square divided by 3, which is equal to 14 by 3. This is how we need to calculate the variance. So in variance you can say it's x variance is also there and y variance is also there. How we can calculate the x variance of this particular three data? So x variance is the distance is 2 square and the center is 0 square and plus 2 square, it is 8 by 3. And y variance, for in this case the mean is the y variance, the mean is at here, so just 0 square plus 1 square plus 1 square, you will get 2 by 3. This is how we need to calculate the variance. Now we can get into what does it mean by covariance. In this covariance, I have considered 5 data points. The first data point is 0, 0 and second data point is 2, 1, 2, minus 1 as third data point, and the fourth is minus 2, 1 and fifth is minus 2, minus 1. And I am going to take the product of all the coordinates. If for example minus 2 into 1 is minus 2, and 0 into 0 is 0, 2 into 1 2, 2 into minus 1 minus 2, minus 2 into minus 1, which is equal to 2. Now for this data, how we can going to take the covariance? See, in this how it is varied, these diagonals are equal, minus 2, minus 2. Same way, the cross diagonals are equal with values of plus 2 and plus 2. How it's apart, how the data are apart from each other. So covariance of first is minus 2 is from the center, it is 0 square plus minus 2. Now we are going to calculate the variance, so we should not take the square, so we need to take the product of the variance, right? So it is 0 0 plus of minus 2 plus of minus 2, you will get minus 4 divided by total number of data point is 3. So here on the another set of data for covariance, which is equal to 0 plus 2 plus 2 divided by 3, so you will get 4 by 3. So the definition of covariance is total variation of two variables from their respected values. So in mathematical way, the covariance of x comma y, which is given as sum of xi minus x cap yj minus y cap whole divided by n. This xi indicates the values of the x variable and the x cap indicates the average of the x variable, and y cap indicates average of y variable, and yj indicates the values of y variable respectively, and n be the number of data points. So kindly pause the video at this particular point and calculate what's the covariance of this particular data points. In this I have considered 9 data points. Pause the video over here and type the answer in the comment box below. If you calculate the answer for this particular slide, you will get the covariance as 0 divided by 9, which is equal to 0. And in covariance types, you have three types, namely positive covariance, negative covariance, and zero covariance. In positive covariance, if you see, both the values gets increases. At together, it will increase. So in x-axis, if it gets increases, y-axis also it will get increase. But in negative covariance, see in x-axis it gets decreases. This is negative covariance gets decreases, but this is your y-axis. So as one variable increases, the other decreases. X increases, your y variable starts decreasing. This is negative covariance. But in zero covariance, there is no, both the data x and y are independent of each other. That is called zero covariance. And now we consider an example of covariance matrix. How to calculate the covariance matrix of a particular data set. In this case, I have considered hours of students that you have studied, and for the particular hours, how much hours they are studying, that much the mark. For 9 hours if a student studies, the mark they achieved by the student is 39. For 20 hours if they study, the mark achieved by the student is 80. So how to calculate the covariance of H and covariance of M and covariance of H comma M, or covariance of M comma H. Now just this is H is hours and M is mark. So Hi minus H hat indicates, this H hat says the mean of H variable. The mean of H variable is 13.92. How Hi minus H hat comes? It is 9 minus of 13.92, you will get minus 4.92. So 15 minus 13.32, you will get 1.08. Same way you just complete the remaining process. So Mi minus M hat, same process, it is 39 minus mean of mark, that is 62.42. You will get minus 23.42. The product of these two columns you are going to write it over here, and the square term of hi minus h hat is comes here, and square term of mi minus m hat square comes here. So how to calculate the covariance matrix? So covariance matrix of h is nothing but variance of h is equal to 5, the sum, the total of the hi minus h hat the whole square is 524.92 divided by total number of data points, in this case is 12. So variance of h is, that is covariance, and variance of h is 43.74. Same way variance of m is nothing but this is variance of m. Here you will get 4070.92 divided by 12. So it is approximately equal to 339.24. Now it's time to calculate the covariance of h comma m. So if you calculate, you will get the average as 1352, total as 1352.42 divided by 12, and covariance of h and m, covariance of m and h both are same, so you will get 112.70. Fine, that is the answer I have marked here. And what's in by eigenvalues and eigenvectors? In simple say, eigenvector is a direction. The eigenvectors may be in a line direction, either it may be a vertical line, horizontal line, or at a particular angle. So what's in by eigenvalue? Eigenvalue is a number telling how much variance is there in the particular data in that particular direction. So principal component analysis. So eigenvector, the eigenvector with highest eigenvalue is called as principal component. So every eigenvector has its corresponding eigenvalue. So if eigenvectors and eigenvectors that exist, it is equal to number of dimensions it can able to say. So let's consider A, B, N matrix, N cross N matrix, X, B, N, A, B, N, N cross N matrix, and X be the, these two X be the eigen vectors, and this lambda be the eigen value associated with eigenvector X. How to find the eigenvalue of lambda? So you need to calculate the eigenvalue, equate the determinant of A minus lambda I to 0, and in this case I is nothing but your identity matrix, right? And we need to equate to 0 like this. Determinant of A minus lambda which is equal to 0 will give you the characteristic equation, and then from that characteristic equation we could able to find the roots of that particular characteristic equation. How to find the eigenvector? It is to use the value of lambda in the equation A minus lambda I into x which is equal to 0, and we can able to find the eigenvectors of the each case. Now we can consider an example of covariance of 7, 2 and 2, 4, and for this particular matrix we get the eigenvectors and the eigenvalues are 2, 1 and minus 1, 2, and eigenvalues are 8, 3. We can see how we can achieve this in another slide. And for this case consider 2, 1. So if you consider 2, 1, the eigenvalues vectors will be over here for 2, 1, and if you consider for minus 1, 2, you will get minus over here in negative side minus 1 and 2. Fine, this both vectors are perpendicular to each other, and the eigenvalue is of first case is 8, and second case is not that much length, you can reduce it over here, you will get it as 3. Fine. So how this is gets transformed? This value is transformed with, this is a circle value, now it's transformed to an ellipse. From 0 to ellipse, this in this magnitude, the magnitude is 8, and in this case we consider the magnitude, it is just 3. And which magnitude principal component says, you need to choose the highest eigenvector. So in this case the highest eigenvalue is 8. We need to consider 8 and we need to throw down number 3. We can see one by one. So for example, if we consider x comma y as 0 comma 0, so this 7x plus 2y plus 2x plus 4y becomes again 0 comma 0. This 1 comma 0 on left hand side point is transformed to 7 comma 2. So for rough purpose I have drawn like this, but don't consider the x-axis and y-axis value. So same way if we consider 0 comma 1, you will get 2 comma 4 and so on. If we consider the eigenvalue as 7, 2 and 2, 4 as I said earlier, So it is A minus lambda I. So A is 7, 2 and 2, 4 lambda, and Y is the identity matrix. It's 1, 0, 0, 1. So if you simplify this, you will get 7 minus lambda 2 and 2, 4 minus lambda. And if you simplify, you will get the characteristic equation as lambda square plus 11 lambda plus 2 24, which is equal to 0. And if you take the roots, you will get two values. One is lambda 1 equal to 8 and lambda 2 equal to 3. And for lambda 1 equal to 8, we need to go with lambda 1 equal to 8 and a minus lambda I, and I am going to replace this lambda with the help of 8 and a minus 8I, which is equal to 0 for x. And if you simplify that, you will get 7 minus 8 of 2 and 2 minus of, and diagonal alone you will need to subtract the lambda 1 value. So 4 minus 8, which is equal to x1 x2, which is equal to 0. If you simplify, you will get minus x1 plus 2x2, which is equal to 0, and the second equation has 2x1 minus 4x2, which is equal to 0. So what value if you substitute for x1 and x2, so that the left hand term will become 0. So if you substitute x2 equal to 1 and x1 equal to 2, this term becomes 0. So your eigenvectors are 2 comma 1. Same way, if you try this, you will get the same answer. And in order to normalize this eigenvector, let me take the square root of the vectors. So it will get 2 square plus square root of 2 square plus 1 square, which is equal to square root of 5. So v1 vector, which is equal to 1 by square root of 5 into 2 1. So the normalized eigenvectors are 0.89 and 0.45 if you round off to 2 decimal. Same way, consider for lambda 2 equal to 3. So same way you proceed and calculate the value of x2 and x1. So eigenvectors is minus 1 comma 2 for both cases. So the normalized eigenvectors are 0.89, 0.45 and minus 0.45 and 0.89. So this minus sign, we can change the notation of 0.45 or minus 0.89. It is possible in eigenvectors, since it is possible in eigenvectors. So what is the principal component analysis? The purpose of PCA is to compress a lot of data into a small data. While you are compressing this into small data such that the compressed data captures the essence of the original data. That is, x dimension is converted into 3-dimensional or 2-dimensional or 1-dimensional. That is the purpose of PCA. We need to compress the large data into small data without losing the essence of original data. So how is dimensional reduction is useful? So there is a risk of overfitting, and the data processing higher dimensional involves high time, and space complexity is very high, and computation is very costly. So not all the features in the data are relevant to the particular problem. So some features may are more relevant to than others one. So the processing may be done for the more relevant features only without significant loss of the information. So for the same example, what we have done, considered for matrix of 7 2 and 2 4, the eigenvalues are 8 3 and eigenvectors are 2 1 and minus 1 comma 2. So in this 3 and minus 1 comma 2 are very least one, so we are going to omit that. So consider the axis, and this was your data, and for this was the eigenvalue of 8, and this line indicates eigenvalue of 3. So which is higher? 8 is higher, so we are going to omit the number 3, and I am going to extend number eigenvalue of 8th line. So we will get like this. Now what I am going to do, I am going to project all those data on that eigen vector. So like this, like 2 1 and 1 2 1 eigenvalue vector, I am going to project all those data points. Now the 2D data is converted into 1D like this. Now 2-dimensional data is converted into 1-dimensional data. So this is the concept behind principal component analysis. Thank you. We'll meet in another video.